Is this microphone working? Okay, perfect. Yeah, so I think my talk is going to be a bit different, actually a lot different from the other talks that we have been seeing so far. And there's actually just two things that I want to convince you of. First of all, astronomy is cool. And second of all, we have plenty of problems that you might be able to solve. So we actually desperately need your help with solving our problems. So if you remember anything from this talk, please remember this. And if you ever have a solution that is in need of a problem, I'm pretty sure that I will be able to provide you with a problem or a nice application. Yes, so I haven't done, well, I've done nothing alone in my life ever. So I had the pleasure of collaborating with all these wonderful people here. Just wanted to highlight Thomas, who is there with us. We also had Silke and Marie. I hope I will get to the end of the slides where I can talk about their work. They're actually astrochemists, so also will be a bit of chemistry in here. And of course, very happy to have John as one of my collaborators. Cool. But first of all, let's try to introduce the subject and give you a bit of background and sketch the context a little bit. So, what is astronomy and astrophysics? So I'm only going to show you like a very narrow introduction to the particular things that we happen to be interested in Leuven. One thing are stellar winds, and the other things are supernovae. But these actually give us a pretty nice idea of how stars evolve. So the subject in general is what we would call stellar evolution. So I'll try to introduce you the what, why, and how of stellar evolution. Cool. So first thing you need to know is that stars evolve. So they are not eternally there. They are actually born and they die. They're born when you have these giant molecular clouds that collapse under their own gravity. And once they're dense enough, you have these kernels that actually start where nuclear fusion reactions can start. And that's when we actually say that a star is born. But another important thing to note is that up until, well, actually quite recently, so like only a decade ago or so, which is, well, recent in astronomy, we thought of stellar evolution as just, well, we described the evolution of individual stars. Whereas it actually turns out that almost all stars appear in either pairs or triplets or quadruplets. And so that's actually very wrong, in a sense, to consider the stellar evolution as just the evolution of this single object. We always have to take into account the other objects and how they interact with each other, which unfortunately complicates the problem quite a bit. Okay, yeah, so now everything has collapsed into these two stars here. Another thing you need to be aware of is that dying stars lose mass. So this happens in these kind of outward directed stellar winds, as we call them. And in doing so, they enrich the universe with their chemicals. So, well, most of the universe is pretty empty, so not a lot of interesting chemistry can happen in there. But in these stellar winds, there's like right about the right amount of density and just about low enough temperatures that you can actually sustain, well, you can actually get some chemical reactions and some reaction products that can actually survive in these harsh conditions. There's also, I should also mention massive stars here, which are like stars more massive than 8 times the mass of our sun, and they can actually undergo core collapse and then yielding these supernovae, which is kind of a more extreme version of this mass loss that I talked about before. But as you see, like the supernovae are kind of out of scope of my slides and this talk, so I will mostly focus on stellar winds. My next role, I will try to study these supernovae. But that's for, well, perhaps the next school. I don't know. Cool. So, yeah, why do we study stellar evolution? Why is it interesting? First of all, I think, well, the main argument that we can make is that it tells us a lot about the chemical history of our universe. So I have here a periodic table, and for all the elements, you can now see how they kind of came about in our universe. So the different colors show you the different production or origins in some sense. So in green, you have here these asymptotic giant branch stars, which are these, well, stars that have these lower mass stars that have these stellar winds and that produce, well, that I was talking about before. And then in red, you have these supernovae. So if you oh no, well, the core collapse is like the blue. So if you see like the green and the blue, that's almost all elements. If you want to know anything about any of the more interesting elements that we have in the periodic table, you need to consider the evolution of stars to know how they actually came about. And if you can discuss the chemical history, it's also, of course, important for the chemical future, because whatever you build will form the building blocks for the next generations of stars and planets. And of course, I have to mention life, but well, we don't really know whether that's a thing or not. And if that's not enough motivation for you, I can also tell you that in doing so, all the simulations that you get, all the data, the observation that you need to reduce, in all of that, there are a lot of problems that allow for beautiful math, data science, and engineering solutions, which is probably the reason why you want to be interested in any of this. Cool. So that brings us to the how. How can we now study stellar evolution? On the one hand, of course, we have these observations. So that's, well, already quite old at the moment, but this is, for instance, an observation of one of these stellar winds. So the actual star is somewhere hidden behind this white dot here in the middle, and what you see is the outflow of material. In this case, it's in particular the carbon monoxide material that you see floating around these stars. Yeah, the actual way in which we do these observations is quite an intricate mathematical problem, which I could talk about, but I won't, just because, well, there are other, well, we have other more pressing problems at the moment, but that's actually also an interesting problem. Cool. On the other hand, we have also simulations of these things. That's something that we're particularly working on in our group. We try to see if you have like a central star in the middle, which is losing all of its mass, and you have then this companion stirring up this outflow. What kind of shapes can you get? And as you can see, this can quickly get quite intricate. But then the question, of course, is what can we learn by looking at these structures and shapes from the actual pair of stars that we have in the middle? Yes, okay, so what comprises one of these stellar wind model simulations? There are many components involved in this. The most obvious component, I think, is the hydrodynamics, right, where you describe actually what are the motions of these gases that we have here. There's actually much more. We also have the radiation transport that we need to care about, because it's actually a very efficient way to transfer energy from one place to the other. On the length and time scales that we're considering, speed of light is well, infinite. So this is actually something that we need to model separately from hydrodynamics. And then there's also a whole bunch of microphysics and microchemistry going on. So in every cell or in every particle that we have in these simulations, we need to care about the quantum statistical state, by which I mean, so this is all rotation and vibration levels of all these molecules, because that's going to determine what the properties are, so the emissivity and the opacity, so all the radiative properties of the medium. Then there's also the chemical kinetics, so if we want to know how much of each material we have at each point, we also need to somehow trace that in some way. Well, yeah, and now what makes this problem difficult is that we have to do all of these things at the same time to have somewhat an idea of what the things are that we can observe. Yes, and in particular, I will now, so the most computationally heavy aspects of the simulation are radiation transport and chemical kinetics. So that's what I will talk about in a bit. Another thing you can note is, so here on the right, you can see one of our models in which we tried to simulate the observation on the left, and what you should notice, it's not a very good simulation of the thing on the left, right? Well, it kind of has these arcs and these, well, it shows similar structure, but it is definitely not the same thing. So yeah, we also want to study this problem from a very different perspective, because yeah, how can we learn something about our models if we can't directly compare them to observations? And to that, to try to solve that problem, quite recently we delved into another kind of, well, area, let's say, with this recent paper, where we tried to forget everything we thought we knew about our hydrodynamic simulations, and we just focused on the data. And we asked ourselves, what model, well, or what would this thing look like? Can we somehow derive a model just by looking at the observations? So that's something that we were able to achieve for, well, some simpler data in this paper. And this is actually an early result of the reconstruction of this particular observation. That is not published yet, but that gives you an idea of what we can actually do with our reconstruction models. And that's also a thing I would like to get to in the end, because I think in particular for, the application that you might be interested in, this is something that we need your help in a lot. Cool. So why do we need probabilistic numerics in astronomy and astrophysics? Well, there's many more, I'm sure, but these are, I think, the main points I'd like to focus on. So first of all, is we need fast or approximate, but quantifiably and tunably accurate models. What do I mean with that? So yeah, the things you want to do are computationally expensive, so I think it's quite a given that we want our simulations to be fast. Therefore, we are aware that we need to approximate things, and we need to cut some corners here and there. So we can accept that, but only if we then can quantify the uncertainty that this implies on our results. So that's why we want these quantifiably accurate models. And also the tunability of the models is perhaps interesting, because it's one thing to be able to run a giant simulation and be able to just have one simulation, but for some of our population studies, we just want to want to have the levers that we need to pull in order to make these simulations a bit faster. Because for some things we can get away with quite approximate results. So it would be nice if the whole thing would be tunable in a sense. The second point is perhaps for you even more important. That is that we need to acknowledge that in our simulations there are very large uncertainties on various input parameters, actually on all input parameters that we use. On the one hand, so for the radiative transfer, for instance, that all relies on spectroscopic data. And spectroscopic data is, difficult to get, and is also it's very uncertain. You have to measure it in a lab, and the conditions that we have in labs to measure these things are often very different from the conditions that you would get, in the neighborhood of a star. So it involves many very, dangerous extrapolations. So yeah, we have large uncertainties on anything that we have in our models. Same story goes for the chemical reaction rates, although I'm slightly more optimistic about those. And then finally, if you remember the last thing I showed you where we tried to make these reconstructions of these observations, we know our observations don't constrain our models enough at all. So the resulting reconstructions will be very degenerate. We'll have many possible solutions that will correspond to a single observation. So we need to be able somehow to navigate this large space of possibilities. Also there, probabilistic numerics can hopefully help us in doing that. Cool, yeah, so there's a few things to note along the way, which is probably different from other things we have seen so far. So typically the problem scale, or the problem sizes that I've been talking about here, concerns millions or billions of particles or elements to have one single stellar wind model. Also, there are many very different components all working together. You have the radiative transfer, you have the chemistry, you have the hydrodynamics, all very different things, and I'm not sure we will be able to address all these problems at the same time. So once we have a probabilistic numeric result in one of them, it will be important to be able to translate or propagate any type of uncertainties we have in one on one simulation through all the other and see what the results are in the end. So I think the uncertainty management will be something that's, something that we need to think about. And also, I think almost all problems that we have in astronomy are, in a sense, nonlinear, which is unfortunate, but that's how it is. We can't do much about that. Cool. So now I just want to go over a few applications, and the first one is actually something that we managed to do, or something that was closest to my heart, and that's radiation transport. So why do we care about radiation transport? It tells us, so it's radiation electromagnetic radiation in this sense, right? So that's just light. it helps us answer the question like how would models appear in our observations. So that's how we get our data in a sense. So that's obviously important. But it tells us also a lot about the internal dynamics of our simulation. So it also informs us, or it's a very important component in how our simulations actually work. For instance, radiative cooling, something that's very efficient in astronomy scales. Also photochemistry. Yeah, so the space is quite harsh when it comes to photochemistry. You can burn quite easily with all the UV radiation that is there. So that's something that you really need to take into account. And then also, radiative pressure on dust. So, how can I tell that story? Okay, the stellar winds I was talking about. So one of the things that actually the main driver that we think that is pushing out these winds from these stars, so that's the cause that why they're losing these outer layers, is exactly this radiative pressure on dust. It's quite a complicated process, or we're not really sure how it exactly works, but that's kind of our best guess at the moment. So also there, radiation plays a critical role. All of this just to say that when you can do something in radiation transport, you're doing well for astronomy. So hopefully that's enough motivation. Now, why or how do we then solve that? So how do we describe the radiation field in one of these systems? So we typically have this equation, which is the radiative transfer equation, where I denotes the intensity of your radiation field, n with the hat is the direction, so you describe light in certain directions, and x is just the location you have in your model. Then, so the first part is just like a directional derivative, so you're describing the change if you walk in a certain direction, and then the change in your intensity is given by this first term, which is your emission, so anything that the medium adds to your radiation field, minus the absorption, so anything that is basically absorbed by the medium. And then there's a last term, quite a nasty term with an integral, which describes the scattering. So if you only consider the first part of the equation, you see that you could describe this all in just by considering one direction. But once you add scattering, you will have radiation from other directions that can basically be scattered in your line of sight, along your ray, or out of your line of sight. For just in the interest of simplicity, I'll just ignore this scattering part for a minute, because then we can do a pretty nice thing. We can write this equation into a formal solution by first defining the optical depth. So optical depth gives us a set, that's actually the relevant length scale when talking about radiation in general. So it's basically the integral of your absorption over a certain distance. And then given that quantity, you can define your intensity, or you have it like a formal solution of your intensity, which is basically just an integral of your emission, but weighted with this e to the minus optical depth. So that seems simple enough, I hope. And now what we went on to do is, given this pretty simple setting, we looked at how we can view this problem as a Bayesian linear regression problem. And we wrote this paper, together with John. And, there were many things that we need to address in this paper. First of all, since it was for an astronomy journal, we kind of needed an intro into, probabilistic numerics, or what the ideas are for astronomy. In retrospect, so I had to reread the paper to do this thing. I'm not sure whether we did a very good job. I would want to do like a new version of it at some point, but I'm not sure. I feel like I'm now in a better place to write the paper. Anyway, yeah. So part of it was the idea was like have an ANA intro to PM, and then the other thing is like okay, we want to show what we can do for radiative transfer. So I say they're a Bayesian linear regression problem, but actually it's just two separate problems. Because first you need to compute your optical depth, and then you need to compute your intensity. As we'll see, these are actually two quite separate things. This is, a slide full of formulas, but we have seen them already many times this week. It's at least consistent with some of the notation I have seen this week, so, but I hope it is familiar, hopefully enough, for most of you just to see what we want to do here. So if you remember, we had these two functions. We had this absorption and this emissivity. what we're going to do in the first step is just do a Gaussian process interpolation for them. Well, yeah, no, that's basically what we do. So we want so we have a bunch of data points along the ray, so positions at which we assume to know what the emissivity or the opacity is, and then we want to get like a continuous description of these two variables. And the continuous version of the function, the interpolant function, is given by these means of this Gaussian process. And then, because, well, we can do this all in a probabilistic setting, we get these nice covariance kernels for these results. So that's all, I guess, like pretty standard. We have seen that a few times. And as a result, we can get then these two conditions means and these two conditions covariance kernels. Nothing much of a surprise there, I think. The only thing that is important to note is that, so we get here a distribution for the optical depth and also one for the intensity, but conditioned on the optical depth, which in our simulations is not necessarily what we want. We don't want to condition on the optical depth because we don't know the optical depth in the first place. So we need to incorporate an additional step here. So we need to marginalize over the optical depth, which turns out to be just about feasible for the setting in which we are working. And the results actually, just from a formal point of view, I didn't write the actual results here, but I just tried to get an idea of what it looks like. So in this notation, the total expectation is actually exactly the same as the mean for your intensity when it was just conditioned on, well, when it was still in the conditioned form. But only here now we have an optical depth with a hat. And well, for the variance, also, yeah, for simplicity, you can like define an upper bound for it. It's kind of similar to what we had before, but you get like these two additional terms. Now, what is interesting about this is that, so the results that we obtained for the two separate problems, that I think I had on the previous slide, so these things, these formal solutions for optical depth and for intensity, that's known, that's not surprising at all. But what is surprising is that once you start conditioning on these optical depth, you actually have a different formal solution. It looks like, instead of the optical depth that we used before, it's actually dependent on another quantity, not the regular optical depth, what we call the effective optical depth, which is defined in this way. So which is slightly smaller, and which is actually reduced with this, with the diagonal of your covariance kernel. Which is, well, to me at least it was surprising, because this is not something that you would just expect from looking at the physics. And which is a result which is interesting, especially for other people working in radiative transfer, or who are working on doing this with, well, in radiative transfer, there's like different schools of how you could actually solve the problem. One school is like in Monte Carlo methods, where you actually propagate your particles through, and the other is just by direct solvers. And so this is actually quite an interesting result for the Monte Carlo methods, because it kind of gives you an idea of how your optical depth, or the quantity that we think is of interest to us, is actually perhaps not the quantity that we're kind of underestimating our optical depths if we estimate them in a probabilistic sense. I guess that's the point I want to make. So even in this very simple setup, which seems like it's basically the most simple thing I think you can do in astronomy with probabilistic numerics. Even in this very simple setup, you can already obtain quite surprising results, which can actually inform the physics and give you another perspective on what physics is going on. Namely, that optical depth is perhaps, if you look at it in a probabilistic way, not the exact quantity that we might be interested in. So then we, of course, did some examples with this. This is probably, less of an interesting slide for you guys, but if you show this to an astronomy audience, they're always very excited that you somehow are able to get some confidence intervals on your resulting computation. So that's, I guess, here for this audience, this is not very exciting. In astronomy, like this, a big deal. Cool. So where is the added value of probabilistic numerics in all of this? So yeah, first we did obtain in this way a fast approximate and quantifiably accurate tunable model. So there's a thing I didn't discuss, but it is in the paper, where once you have your Gaussian process description of your problem, you can also map it to feature space and solve it there to get like a reduced order model for it. And then by the number of basis functions that you use, you can kind of get a handle on the complexity of the problem, which is pretty nice, but it's, well, I'll come to that later. And then the other thing, yeah, we can model the impact of uncertainties both on our input and on our discretization. What these uncertainties mean and whether they are actually informative is something that I struggle with at the moment. So we haven't calibrated our errors or uncertainties in any, well, not yet. So that's something that I think, yeah, that's very much something we should do at this point, which I actually learned about here this week. Currently, another main issue that we have is that, well, the large computational cost, because we have this covariance matrix that we need to invert in principle. But then on Monday, we learned about how we could replace this with an iterative Gaussian process, how we can use this iterative approach to actually solve this. So I'm now, well, I haven't tried to think how we could actually implement this, and I think this, well, this is definitely something we should try out, and well, something that I will look into. Cool, so that's for radiative transfer. That's something that we have been doing so far. After that, we have also been looking at chemical kinetics, because I think there is also, well, there are also plenty of opportunities for PN. But these haven't, so everything I will say from now on hasn't been done yet. So if you see something you like, please go on and we'll do it. That's basically what I want to say. So what does chemical kinetics actually do for us? It tells us how much of a particular atom or molecule, or chemical species, is present at a certain point in our simulation. It's described by a set of coupled nonlinear ODEs. They look like this. That's not very, well, it's not, it looks a bit complicated, but it's actually not. So you just describe the change that you have in your abundance of a particular species I, and then that change is given by a bunch of production reactions and a bunch of destruction reactions, which are just written in this funny way so that you can combine the abundances of the relevant species, and then they're all, well, the reaction rate is then given by this factor K. Just to give an idea, oh yeah, and then if you just run this, so this is like a typical thing we would be interested in. So we're looking at CO, water, OH, and a whole bunch of molecules that we want to model throughout our star widths. Now, to put this thing into perspective, because this is a nice equation, but what is not nice about it is that we have to solve this for about 500 species. Now we have about 5,000 non-zero reaction rates in this network, which makes it quite stiff and a nasty problem. Yeah, and then if you manage to solve this for one point in your entire simulation, you then have to do this for every point in the simulation. And to give you an idea, so these are like millions or billions of points. So this is, yeah, unfortunate and difficult, but luckily, okay, perfect, thank you. So one of our PhD students who will defend in the summer, so Silke Maas, came up with a solution for this problem, inspired by machine learning. So and this is a diagram of what the solution would look like. So on the left here, I have what the input would be of our chemical kinetics, and on the right-hand side, this is what the output would be. Classically, what you would do is you would get like a set of initial abundances, and you would solve well, yeah, the relevant differential equation, and then you will get your abundances at some later time. What this new method actually does is that you put this whole thing into an autoencoder. So you first encode. So this is a neural network. Doesn't have to be, but it is at this point. First, you encode your sets, your abundances of your chemical species to a lower dimensional latent space. Let's call that Z for the moment. And then you solve some kind of latent or surrogate dynamics in this smaller dimensional space, which you also try to learn at the same time. And then once you have, so then you evolve in this lower dimensional space, and then you, at the end, decode again to get your full chemical output. So what is nice about this approach is this actually works. We were quite surprised that it worked this well. What is less nice about this approach is that it's hard to quantify how well it actually works, and even more difficult to answer the question how well we want it to work. Because, of course, yeah, what you can do is you have this and you can compare it to what your original model does, but we don't know what the uncertainty, well, how well or how much we can trust our original model in the first place. Especially because here, all these A and B now codify these reaction rates. We don't know what, well, we know that there are large uncertainties in those, but we don't know what the effects are on the timescales that we are actually interested in. So it might as well be that we can, well, so we don't know how far actually we can reduce these chemical models. And of course, the amount of reduction that you can do on this side will influence the error that you get with respect to the original model, but we don't know how much error that we can get away with. That's very difficult to explain that to a reviewer in an astronomy journal. Perhaps even more difficult to get it to a reviewer in a mathematics journal. But yeah, that's something that we struggle with at the moment. So now we can get like a speed up of a factor of something 20 to 60. But what we need to make this whole thing feasible is the factor of 1,000. And that is doable if we just can shrink our latent space enough here. And we can get like, well, it might be possible. So we might have solved this problem with this approach. It's just that we don't know, well, yeah, how far we can push it. Because we don't know how much we can trust our original models in the first place. So yeah, here, having proper uncertainty quantification through all of your simulation can really make the difference between being able to do a simulation with chemistry or just not being able to do it because it would take forever to run anyway. Cool. Yeah, so there's plenty of opportunity, I think, for PN in this area. So modeling your large uncertainties. Yeah, model the impact of dimensional reduction, and probably also you can inform the dimensional reduction process if you would have PN in this. But I basically said that already. Cool. And then finally there is, yeah, this problem of Bayesian model reconstruction, where, yeah, the question is like how to create realistic 3D models. Yes?
Can I ask a question about the previous application? Do you have data set from experiments that people actually did that kind of simulate these reactions to get the percentages of the chemical elements? Or is this purely based on you evaluating against the classical dynamics? I guess what I'm asking is there experimental validation data so you could, you know, check whether your model that is not as closely tied to the classical dynamics performs better than the classical dynamics?
Yeah, the way that we measure these reaction rates is actually by measuring the reactions. So that's kind of the way in which these reaction rates are measured in the first place. The big problem there is that the conditions that we're interested in are very different from anything that, well, from most things that we can recreate in the lab. The regime in which we're interested in this chemical kinetics is in a very far out of equilibrium, where you have like in these outflows that you have all these shocks and all propagating through. And in the lab, when you want to measure these reaction rates, usually you want very controlled circumstance with a constant density, constant temperature. You try to like measure the environment as good as possible to know what these reaction rates are. So it's difficult to have an actual experiment that is relevant for the cases that we're interested in here below. And that kind of holds for all the things and all the reaction things that we measure. The way in which we measure them, or the situations in which we measure them, are very far away. So everything we do is extrapolation, and that's, well, difficult. Yes. So the last application was about this model reconstruction, where we want to create realistic 3D models are, well, in the language of yesterday, and hopefully at some point we might be able to use a digital twin for particular observations. Because to put this into perspective, there's only a handful of objects for which we actually can make these high-resolution observations. We have like about 15 of them. And so 15, 1, 5. And these are very well studied. We have plenty of observations for them in various frequency bands, various different things. So it might actually be feasible to make, well, specific digital reconstructions of these particular objects. We now did it only for the CO already, so for the CO cloud around them. But yeah, it's, what do I want to say for this? Okay, yeah. The way we did this, but that's probably going to lead us a bit too far. Yeah, we just basically did, we wanted to maximize the posterior likelihood for these things. And what I think where PN can help here is that it actually could help us by providing us with the likelihood. Because usually when you do these kind of things, you just, well, yeah, you have a simulation, and that simulation, then you assume that the uncertainty on that is Gaussian. But if you could have a proper probabilistic numerical model for your radiated transfer, so that would be this part, you could actually have a much better likelihood than just something that is a simple Gaussian. Another thing is that, yeah, the physics provides us with a prior, and you can do a whole lot of funny things with physics in priors, but I actually don't dare to show them here because I think that many of the priors are actually very, very ill-defined. But if you want to have a good laugh, like look at wave radius. I think for mathematicians it must be a lot of fun to look at what we actually try to do. But if you have a solution, please let us know. Cool. So what are we doing? Yes, so we can use PN to model the large degeneracy that we have in our models, and hopefully get a better idea of the likelihood. And I think, yeah, that's about all I wanted to say here. I think I said all that, yes. So we showed radiative transfer, chemical kinetics. We have many uncertainties, and we need to model them. And yeah, having uncertainties or not having uncertainties can really make the difference between being able to model something and, well, just not being able to model something. So we really, really need your help. Thank you.
Fred, are there any questions?
First of all, thank you for the talk. I have a question about the first point you just showed at the end, just to understand the value of these methods for astrophysics. So, is the first point only about, okay, I want the most accurate model for a given time budget that I have? Or is it also about, I have a process where I maybe want to run it at lower resolution more cheaply, then I do something, make another observation or something, then I run it at high resolution again. So I actually need to tune, I need to tune my accuracy of the model, and I find the lower accuracy solution initially, because I don't know, I set up my measurement device in a specific way.
Yeah. So in astronomy, observations are very slow. So I don't think that the real time, but I'm not sure exactly where you want to go, but in many cases, we are very happy with very approximate results. So for many of our simulations, we just want to try things out. So it would be very interesting if we could just try with something that is very low accuracy and then like gradually build up wherever we need more accuracy. If we do like large population studies, then we need to have many models. Some of them accurate, others less.
So there's like this human in the loop component where you look at the low accuracy solution, change something, run the model again, maybe with high accuracy, so it takes longer.
Yes, yeah.
Thanks for the talk. Very interesting. Can you show this that beautiful figure there, observation distance instead? How can you explain what is this color represent, the different colors, for instance?
Oh yeah. So on the left-hand side, the color that you see is, so the red parts are the redshifted things. So these are the things that actually are moving away from you, and the blue things are the things that are moving towards you. So this is not in real colors. So what we actually observe are, I actually have a slide on that. So what we observe actually are spectral lines. So, and the nice thing about spectral lines is they are of a very narrow extent in frequency space, which means that if your source or the material or part of your source is moving at a certain velocity with respect to you, you can see the Doppler shift of that emission, which kind of gives you this tomography of the material moving at different velocities. First, it's easier to look at the still image. So here, this is for different velocities, the material that is actually moving with that velocity along your line of sight. It's by combining all this information that you can like get the 3D model. Yeah, so I guess if I show it in this way, oops, where is it? Yes, here it looks like a bit of magic because there's not that much information in this image. You actually have more information because we have all the different frequency channels that we can use to create this.
Yeah, thanks also from my side for it's a nice application. I was wondering, could you go to the slide with the Leuven quarter focus? Because I understand you say that your classical dynamics model, you're not even sure if that's somehow correct. Is that right?
That is, yeah, that's currently an issue, yeah.
But this is a model that you arrived at from first principle?
So it is, yeah. So there are some first principles in the way in which we compute these reaction rates, but all of these principles have measurable constants. Like the actual reaction rates, how they're measured is in very confined circumstances, you try to like measure what the actual reactions do, and then you use that informally to compute these reaction rates. So it's partly empirical, but there are some, yeah, it's physics informed in a sense.
But it's not sure if this model actually accurately captures the true state of the nature.
Well, it's not completely crazy. Like for instance, in combustion chemistry, like there are engineering applications where these things are modeled like crazy, and where we have like many applications where these things work very well. But yeah, SAR is different from an engine. So we misuse some things in a way here, yeah.
The only reason why I asked is because would it be much simpler to start with a simpler model and then work up to larger, more complex models? Then it seems like it's a really complex model and you're trying to simplify.
Yes, yeah. I don't know the history of the chemical, well, how chemistry did this actually well enough, but at some point, yeah, the simpler version of this is if you take a thermodynamic limit of your system, everything becomes much easier. And I think so we have like, equilibrium models for all this chemistry, which work nicely up until some level. So I guess, yeah, there are limits in which this actually is very, there is a limit in which this simplifies quite nicely, also in a physical sense. Yeah, and then this is kind of the extension out of equilibrium to what we want to do. But yeah, there's also a debate on how much non-equilibrium we actually need to do things. That's the part of the problem.
Okay, in which case let's try. Oh, sorry.
Is there any algorithm or whatever model that currently doesn't work, but you wished you work? You know, like a piece you find, I really would like to have this work efficiently, or some specific maybe.
What is where to start? Is that the question?
Yeah, maybe it's whether there's like some algorithm or model you really would like to have, but currently you don't have. That's somewhat realistic. A wish, maybe.
Yeah, I think starting from the radiative transfer, so the radiative transfer is really a key part in all of this. I must say I'm a little bit biased because that's what I did my PhD on, but because that is really the part that both connects our simulations to observations and is important within the simulations itself, because it influences many of the separate components. So if we have like this tunably accurate, tunably and quantifiably accurate radiative transfer model, I think that's kind of the holy grail. And Thomas, who's sitting right in front of you, is actually tasked with part of that problem. So,
Okay, so let's thank Frederik again.